So everything we do today is going to be actually a good chunk of kind of repeating some of the things that we've already done. Okay, so it should be good to kind of just re-emphasize all the things we've done, because we've already done Taylor-Maclauren polynomials, right? A polynomial has a stopping point, right? It's either a 5th degree polynomial, a 6th degree polynomial. A series goes on forever, right? So a Taylor series is where you never stop, right? You keep writing the nth degree until infinity, okay? And so you find it the same way, right? You just would never stop writing. So we've done this before, but let's do it for practice here. We're going to write a Maclauren series for cosine. What does Maclauren mean? Centered at 0. And we're going to write it in summation form as well, since it's going to be an infinite series. And then we're going to find the interval of convergence. So we'll review that. So how do I find the first term of a Maclauren series centered at 0? What do I do to find the first term? Plug the center into the function. What is f of 0 here? What's cosine of 0? 1. So we're going to write an equation for cosine of x. And this time it's going to be equal to. It's not going to be an approximation, because if we go to infinity, it will be literally equivalent to cosine. Okay? So the first term will be 1. How do I find the second term of a Taylor polynomial? Take the derivative, plug in what? 0 in this case, because it's the center. So what is the derivative at 0? What is the derivative of cosine? Negative sine. What is negative sine of 0 going to be? 0. So this will be 0 times. And then we always do x minus the center. How will I find the next term? What do I find? The second derivative and plug in the center. What's the derivative of negative sine? Negative cosine. What will be negative cosine at 0? Negative 1. So our next term will be negative 1 divided by what factorial, though? 2 factorial, because we're now on the second degree term, so it'll be x minus 0 to the second degree. So it's the second derivative. It's 2 factorial. It's x minus the center to the second degree, right? It's all 2. Let's keep going a little bit. What's the I'm not going to keep writing out the derivatives. What's the derivative of negative cosine of 0? Yeah, it'll be sine of 0, right? And what's sine of 0? 0. So this will be 0 over, this is the third degree term. So what factorial? 3 factorial, x minus 0 to the third degree. We'll do one more. What will be, the last derivative was sine. What will be the next derivative, the fourth derivative then? It'll be, I think we'll be back to cosine, right? From the beginning, right? So it was sine and then cosine. What's cosine of 0? 1. So it'll be 1 over which factorial? 4 factorial. X minus the center to the fourth degree. And this will continue on forever. Right? So let's write out the a little bit more simplified here. So this will be cosine of x will be equal to 1. This first term, the second term will disappear, right? Because of the 0. What other terms will disappear? The third term. And in general, which terms will disappear? The odd terms, right? They'll all disappear because we'll keep going back in between 0, negative 1, 1, 0, 1, right? Because every sign will be 0. So we'll have minus 1 over 2 factorial times x squared plus 1 over 4 factorial times x to the fourth. And you don't even need to calculate it really, but could you tell me what the next term is going to be?
Minus x.
It's going to go back and forth, positive and negative, so the next one will be negative x to the 6th over 6 factorial, right? At that point, you don't even need to calculate them, right? You can see the pattern. And now we're going to write this as a series because this is infinite, right? This is going to infinity. So we're going to write the summation notation starting at 0 and going to infinity. It's alternating, right? So we'll have negative 1 to some power. It'll either be n or n plus 1, okay? That's still your table. Yeah. It'll either be negative 1 to the n or a negative 1 to the n plus 1. It's just a matter of where do we start, positive or negative, right? So here, what is our first term, positive or negative? And then it goes negative, right? So if we're starting at 0, do we want this to be an n or an n plus 1 to start positive? If it's n, what will be the first one when you plug in 0? Negative 1 to the 0, which is positive 1, right? Then when you plug in 1, you'll get negative 1, right? And we'll continue going that. So we want just an n. Then what's the power on all the x's? Is it just n? Does this go 0, 1, 2, 3, 4, 5? What are the powers of all the x's? They're all even numbers. How do I write even number? 2n. 2n, right? Because then if you plug in 0, you'll get x to the 0, which will be 1. So the first time. Plug in 1, you get 2. Plug in 2, you get 4. Plug in 3, you get 6. Plug in 4, you get 8, right? And then the factorial in the bottom is the same 2n, right? So that is a Taylor series for cosine. Now, you will never do this one again by hand. You should have this one memorized, okay? In a minute, we're going to flip the page over, and there are 4 that you should have memorized, okay? Sine, cosine, e to the x, and 1 over 1 plus x, okay? Those are the 3 you're going to have memorized. So you're never going to probably do this again, but it's good to just practice the Taylor series stuff, okay? Now we're going to find the interval of convergence, so we're going to review what we did last week. This is a series. This is a power series because it's x to a power of n. And remember, to find the interval of convergence, we either run the geometric series test or the ratio test. Is this a geometric series, or do I need to use the ratio test? Ratio test, right? I mean, you've got an nth power, but the second you have an n factorial or any other n anywhere else besides the power, it's not geometric anymore, right? Geometric has to be something to the nth power, okay? So this is going to be ratio. So we'll do the limit as n approaches infinity of an plus 1 in the top. So we're going to plug in n plus 1 in for n. When you plug in n plus 1 to 2n, what will you get? 2n plus 2, right? Plug in n plus 1 there, distribute the 2, and you'll get 2n plus 2. And then, so you'll have 2n plus 2 factorial in the bottom. And then it's divided by an, but then we flip and multiply, so we'll go ahead and flip and multiply. So this is reviewing what we did on Friday. And the only way that this stuff you're going to get better at it is just to practice. And then we start canceling out whatever we can. What's going to happen to these negative 1 things to the n plus 1 power? They're just going to turn into 1 because it's absolute value, right? What happens to that? Those are either going to be negative 1 or 1. And if this is the absolute value, then those are just going to disappear and become 1, right? Always. They will never be negative 1. So those will go away. Can I cancel out this x to the 2n with something? This guy, right? If you separate that into x to the 2n times x to the 2. So when I get lazy and good at this, I just cancel out this and remind myself that's still x to the 2 in the top. And then let's go ahead and write out the first couple terms of the factorials to make sure we get those right. So the negative 1 thing will go away. We'll have an x squared left in the top, right? Because this separates into x to the 2n times x squared. Or what you can do is you can separate it and then cancel that part out. That's another option to make life a little bit faster, but not forget the x squared. And then 2n factorial, the first term will be 2n. What will the next term be? 2n minus 1, right? You always subtract 1 every time you go down in a factorial. And the bottom, this will go away, this will go away. So all we'll be left with is 2n plus 2 factorial. So the first term will be 2n plus 2. What will be the next term? in that factorial? Just subtract 1. What do you get when you subtract 1 from that? 2n plus 1. And then what will the next one be? 2n. And then 2n minus 1, right? And so that's when they'll start repeating. So this guy will cancel out with the whole entire top and the bottom except for the first 2 terms of the factorial in the bottom. Most of the time, I have to write out the factorials to see which ones cancel, unless it's just like n and n minus 1. Those are easy for me to figure out what cancels. So now all we have left is the limit as n approaches infinity of x squared in the top over 2n plus 2 times 2n plus 1. And what is this limit going to be equal to? 0. But aren't these the same degree? X, this is a 2 degree, and when you multiply these two together, that'll be a 2 degree. Are those growing at the same rate?
It's a constant to n.
Good. We're taking the limit as n goes to infinity, right? Not x. So x is just a number, right? Don't pay attention to his degree. He could be 5. He could be 7. He could be negative 1, right? We don't know what it is, but it's just a number. So the bottom is the only thing growing, right? X is not growing, n is. So that'll be 0. What have we been running? What test are we running right now? The ratio test. What does the ratio test say when you get 0? That's less than 1, so it converges. Doesn't matter what x is. That limit's going to be 0 no matter what x is, right? That's what we just said. So this is going to converge for every single x. Right? Doesn't matter what x is, that limit will be 0, right? So this will always converge no matter what x is. So what do we say our interval of convergence is? What is the range of values of x? From 2 to 5? How do we say all of them? All real numbers, negative infinity to infinity. And remember, you'll only ever get negative infinity to infinity, only the center or a symmetric interval around the center, right? Those are your only options. Here, the radius is infinity because from the center to infinity is infinity. Any questions about that? It's basically all review. Okay, so now let's find a Taylor series for cosine of 2x. And this is exactly why you are going to memorize cosine. Because if you don't memorize cosine, you're going to have to do this one from scratch and start with the first derivative and the second derivative and the third derivative and the fourth derivative and the fifth derivative. But I don't need to, because you're going to memorize what cosine of x is equal to. And if I memorize what cosine of x is equal to, then I don't have to do any derivatives at all. I just need to take this equation and plug what in for x? 2x, right? And if you take this polynomial and even the general form and plug 2x in for x, you now have an equation, a polynomial for cosine of 2x, right? Because isn't that what this is? Cosine with 2x inside, right? So now I can use my work from up there and I can say, okay, cosine of 2x is equal to 1 minus 1/2, or I'm sorry, 1 over 2 factorial, plug in 2x for x, 2x squared, plus 1 over 4 factorial, plug in 2x for x, 2x to the 4th, minus 2x to the 6th over 6 factorial, dot, 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 dot. And we can even do it in the general term. Plug in 2x for x, not n, right? And now you have found a series for cosine of 2x with very little work, right? You didn't have to find the derivative or the second derivative or the third derivative because you're taking a known Taylor polynomial, known Taylor series, and plugging in something for that, doing a composition instead. Is that a question, Nathan?
Yeah.
Yeah.
Why doesn't it like change the comp? Because don't you like when you find derivative, you move the 2 in front?
So this will be 2 to the 4th times x to the 4th. So that'll be 2 to the 4th power,
So
which is
it's already doing it. Like,
right? Because if we were to simplify this right here, right, this would be like 2 to the 4th times x to the 4th over 4 factorial, right? And that's exactly going to be all of those 2's that came from doing the 4th derivative. Does that make sense? Yeah. Great question. Okay, so now let's talk about the interval of convergence. Do you think it will change if I just change the composition? Any ideas whether you think it'll change? I like the hypothesis of no. It's not going to change. The only thing you need to be careful of if you do a composition is sometimes the endpoints might get dicey. If you have one endpoint converging and one not, the endpoints could change, but the interval itself should stay the same. And let's see how the interval stays the same just by looking at the end of our limit. If we go up here and do this ratio test again, what's the only thing that's going to change in the ratio test? What's the only thing that changed here? 2x in for x, right? So you'll have a 2x there, but that's still going to cancel everything out correctly. So really, the only thing that's going to change right before you have your limit is this will be 2x squared, right? So that'll be 2x squared over 2n plus 2 and 2n plus 1. Is that limit still going to be 0? If that's 2x squared? Yeah, that doesn't change anything, right? That limit's still going to be 0, which is less than 1. So the interval of convergence will still be negative infinity to infinity. If you do a composition, the interval of convergence will not change, maybe with the exception of the endpoints. If you're checking endpoints, you still will need to check the endpoints. One endpoint might diverge or converge. Any questions about that? Okay, so flip to the next page. And this is a list of common series. You don't have to memorize all of them, but you do need to memorize the ones that have the hearts by them. Okay, so 1 over 1 plus x, e to the x, sine of x, and cosine of x. Okay, because we'll do things like ask you to find sine of 2x, or e to the 5x, or e to the x to the 7th. Right? And all you have to do is plug in whatever's inside that function into that. We'll even multiply things. Like I can ask you to do x times e to the x. And if you know what e to the x is, you just have to multiply it by x, right? So all sorts of things based off of that. You can choose whether you want to memorize the term version or the general term, as long as you can kind of get one from the other. Does that make sense? So if you'd rather memorize the general term and then get this one out of that, great. If you'd rather memorize this one and get this out, great. Or just memorize both, whatever works for you. But you do need to know both forms. Does that make sense? Okay? And then these are the intervals of convergence for them. We'll talk about why one of them is the case here. So let's look at an example here. If I ask you to find 1 over 1 minus x, which one of our series that I told you have to memorize does that look similar to? 1 over 1 plus x. What's the only difference? It's minus, right? So this will be the same as doing one over 1 plus negative x. So if you know the series for 1 over 1 plus x, what's the only thing you're going to have to plug in to 1 over 1 plus x? What will you need to plug in? What's right here? Negative x. So if you want to know what the series for 1 over 1 minus x is, if you know 1 over 1 plus x, just plug in negative x in for x, right? So let's look at that series. It says 1 minus x. So 1 plug in negative x in for x plus, oh, you can't see it up there. Sorry. X squared, so plug in negative x in for x squared, minus x cubed, plug in negative x in for x, plus dot, 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 and then we'll even do it in the summation notation too. So plugging in negative x in here and negative x in for each of these, right? So now let's simplify this down. So this will be minus the negative x turns into what? Plus x. What happens when you square negative x? What are you going to get? What happens when you square a negative? Get a positive x squared. What happens when you cube a negative? You get a negative, but then we have a negative out in front, so what will that turn into? Positive x cubed. And so all the negatives are supposed to go away. So let's see how that works with the summation notation. Okay, so this guy here, you can think about it as a few ways, right? This guy we could break up into negative 1 to the n times negative x to the n. Or if you want, you can just multiply negative 1 and negative x and have x to the n power, right? So you can either separate that out, but then when I multiply these two together, what will be negative 1 times negative 1? Oh, sorry, this should be a positive. Got distracted. So if I separate this out into negative 1 to the n and x to the n, I can multiply those together. Negative 1 times negative 1 is positive 1 to the n. And what's positive 1 to the n?
1.
Yeah, 1 to any n is 1. So this is just going to be equal to x to the n. If you rather think about combining it into negative x, that's another way to do it. All to the nth power to get x to the n. It's all the same. No matter what, this is just going to become x to the n. So we recommend memorizing 1 over 1 minus x because if you know the alternating one, then this one's easy to get, right? Rather than memorizing this one. But you could also memorize this one, and then you would find 1 over 1 minus x by plugging negative x into this one. Okay? So that would be another option. Now, we want to find the interval of convergence for this. They told us the interval of convergence of this guy was negative 1 to 1, so we would expect that this would probably stay the same, but this should be pretty easy to see that the interval of convergence is negative 1 to 1. What kind of series is this? Geometric, right? What's R? Here. X. And when does a geometric series converge? When the absolute value of R is what? Less than 1, right? Geometric series converges when the absolute value of R is less than 1, and that literally means then that X has to be between 1 and negative 1, right? So the interval of convergence here is negative 1 to 1. Remember how we talked about testing endpoints last week? Do I need to test the endpoints here? Why not? It's geometric. What happens when R is 1 or negative 1? It diverges, right? So if it's geometric, you don't have to test the endpoints. It will diverge at the endpoints. So we're getting good review in for everything else. Any questions? Okay. So on the back page, there are a bunch of practice ones where, like, let's just go look at some of these on the back page real quick here. We're not going to do all of these. We probably won't have time to get to any of them. But, like, this is what I mean by you need to have them memorized. For the first one, if we're going to find we're going to have to find a coefficient of the x to the sixth term in the Taylor series. You could start out by just trying to take derivatives. First derivative, second derivative, third derivative, fourth derivative, and go from there. It's on my desk. It should be in one of those top, either the red or the yellow folders on the top corner. But that's a lot of work, right? Especially with e to the 2x squared. So instead, which one could you have memorized to do this problem? If you have e to the x memorized, right, this is the same thing as 1/2 e to the x to the 2x squared. And so then if you had e to the x memorized, what would you plug in for x?
2x squared.
2x squared, right? And then you would multiply by 1/2. And then you have your series, right? And then you can figure out which one, what's the number in front of the x to the sixth term. If you want to do this one, which series should you have memorized? Cosine, what are you going to plug in? Square root of x, right? So for none of these should you actually be finding the first, second, third, fourth, fifth derivative, right? You should not be doing them from scratch. You should be taking one that we have memorized and plugging stuff in. Does that make sense? Which one should you have memorized for this one? Sine of x, you're going to plug in 5x, okay? So these are good practice problems. The answer key is on Schoology for these. We probably won't get to all of them, but they're good practice. So now let's flip back to this question. We're going to do one that is a little more general. So instead of giving an equation for f, they only give us certain facts about f, okay? And so we are going to do this one from scratch. This was actually on the 2016 exam. So there's always a Taylor series question on the BC exam. So always free response. Okay, so we have a Taylor series. We're going to write a Taylor series for f centered at x equals 1. We know f of 1, we know the first derivative, and then they give us a formula for any nth derivative that we want. Okay? So if we're going to write the first 4 non-zero terms and the general term for the Taylor series, let's start with the first term. How do you find the first term of a Taylor series? You plug in the center. What's the center here? 1, so it'll be f of 1. Then how do you find the second term? You plug 1 into what? The derivative, the first derivative. And then you'll do x minus the center, right? You can think about this term as the first power over 1 factorial if you want to. If that's helpful for you. And then how do I find the second term? I need the second derivative at the center over what factorial? 2 factorial times x minus 1 squared. And they want the first 4 non-zero terms, so assuming none of these are zero derivatives, we need at least one more. So we'll do the third derivative at the center times x minus 1 cubed over 3 factorial. And then the nth term will be the nth derivative at 1 over n factorial times x minus 1 to the n power. This is another way to write an infinite series, is to write the general term, not necessarily write the equals with the summation, but just say, okay, any term you want, this is the term. You do the nth derivative, we know it's divided by n factorial, x minus 1 to the nth power. So now let's go ahead and actually find some of these values. What is f of 1? All we have to do is read. What is f of 1? They tell us. What is f of 1? 1. What's f prime of 1? Negative 1/2. How do I find the second derivative at 1? They didn't tell us that one. This tells us how to find the nth derivative, right? Which derivative are we looking for? Second. So what are you going to plug in here for n? So let's find the second derivative. At 1 will be negative 1 to the 2 times 2 minus 1 factorial over 2 squared. Negative 1 squared is positive 1. 2 minus 1 is 1. 1 factorial. So this will just be 1 over 4, but I'm going to leave it as 1 over 2 squared just to show you some stuff in the future. So that's this term. So you'll have 1 over 2 squared divided by 2 factorial. So I'll just write 1 over 2 factorial times x minus 1 squared. And then we need the third derivative. So let's use the formula to find the third derivative. Plug in 3 into their formula for you. Negative 1 to the third, 3 minus 1 factorial over 3 squared, or I'm sorry, 2 to the third. Negative 1 cubed will be negative 1. 3 minus 1 will be 2 factorial. I know you can simplify that, but I'm going to leave it, okay, for purposeful meaning. So we're just plugging it into their little formula, right? We got negative 2 factorial over 2 to the third. We good? Okay, so that's your third derivative. And then it's times 1 over 3 factorial because we're dividing by 3 factorial. And then for the nth term here, we'll just plug in our formula for what, because they told us what the nth term derivative is. So that's negative 1 to the n times n minus 1 factorial over 2 to the n times 1 over n factorial. That's from our Taylor polynomial, x minus 1 to the n. So I literally just plugged in their formula right here, because that's how you find that derivative. And then this is 1 over n factorial times that. So it's a little bit harder to see over here. You can kind of start to see it in this one. You do have some, you could cancel out the 2 here with this, but even better, this is 2 factorial and 3 factorial. So if you have a 2 factorial on the top and a 3 factorial on the bottom, what's going to happen there? The 2 factorial will cancel out with the 2 times 1 part of the 3 factorial, right? Because this will be 3 times 2 times 1, and this will be 2 times 1, right? So this will cancel out with the factorial part of the 3, right? And just leave you with the first term in the bottom. And you can see that here, too, because you have n minus 1 factorial. So if you have n minus 1 factorial, that'll be n minus 1, n minus 2, dot, dot, dot. And n factorial in the bottom will be n minus 1, n minus 2. And so you'll have the top will always cancel with everything except the first term, right? Because this is literally n on the bottom and then 1 less term factorial on the top, right? So by nature of a factorial, this will cancel. So we can see the n minus 1 factorial will completely go away. And cancel out with just the factorial part. So you'll just have the n left. And that's why I left it that way, so you could see that cancel. In the next ones, it would be easier to happen. So let's just write it just slightly more simplified. We won't go too crazy here. We'll kind of leave the first couple terms the same. 1 minus 1/2 times x minus 1 plus 1 over 2 squared times 1 over 2 factorial times x minus 1 squared. Not really any simplifying to do there. We'll leave the 2 squared and the 2 factorial. Here, this will be minus 1 over 2 to the third times 3 I guess 2 factorial is just 2, so we'll leave that as 2. And then we'll rewrite the stuff that canceled out over here. So negative 1 to the n stays. We'll have 2 to the n times just a plain old n in the bottom. And x minus 1 to the n. So if you write it this way, you can kind of see the pattern, right? This is your n here. And then this is your 2 to the power of n. This is a power of 1 here. Everything's to the power of 0 at the beginning, and that's why we get 1. And you can see that general term. Any questions about that? Okay, so now we are asked to find the interval of convergence for part B, but they give us an important fact. They tell us that the Taylor series has a radius of convergence of 2. What's the center of this Taylor polynomial? X equals 1. If the radius is 2 of your convergence, how far does your interval go then? From where to where? 2 this way, which would be to negative 1. 2 this way, which would be 3. So it would be go from negative 1 to 3. That's what the radius is. So is it as simple as that? Is that all I have to do to find my interval of convergence? Yeah. Unfortunately, we have to check the endpoints. Did we run a geometric series test here? No. So we don't know if it converges at negative 1 and 3, right? That's basically equivalent what they're asking us. Does it converge at negative 1 and 3? So we're going to plug in negative 1 and plug in 3, and we'll see what happens. So it's much easier to do the general diversion when you're looking at convergence. So we'll plug it into this guy here. You don't really, it's hard to tell from just adding up the first couple terms if it converges or not, right? You need to run a test on something like that. So we'll plug in negative 1 in here, and we'll get negative 1 to the n. Are we plugging in negative 1 for x or for n? X. So then negative 1 minus 1 will be what? Negative 2 to the n over 2 to the n times n. These guys, since they're both raised to the nth power, I can just multiply them together and raise them to the nth power. So really, negative 1 times negative 2 is what? 2 to the n? Well, that's nice. Because what happens now? Something convenient here? Some canceling. And what are we just left with? 1 over n. I think you know what that does. What does 1 over n do? It's a divergent harmonic series, right? It's p series of p equals 1. So it does not converge at the negative 1 endpoint. Now we need to check x equals 3. So plug in 3 in. You'll get negative 1 to the n. 3 minus 1 is 2. Again, you're plugging it into your general term so you can look at the actual series to see if the series converges or diverges. We don't need to multiply these together this time because what's going to happen with those 2 to the n's? Those are just going to cancel the way they are. So we'll have negative 1 to the n over n. So that's almost the same as 1 over n, but it's alternating. Does that still diverge? What happens when you make the harmonic series alternate? It converges. You can run the alternating series on that. The limit of 1 over n is equal to 0, and that thing's decreasing, right? An plus 1 will be less than that. So this is the alternating harmonic series, which converges. You could run the alternating series test. But you should know by now that thing converges. It's the alternating harmonic. That is the prime example for conditional convergence, because the harmonic series diverges, but you make it alternate and it converges. So what's our final answer for our interval of convergence then? It's not really -1 to 3. Where does it converge at? Which endpoint does it converge at? 3. Does it converge at -1? No, so it'll be -1 not included, 3 included. All right. They tell us that this guy is an alternating series. It should be pretty easiest for us to tell that it's alternating because of this -1 to the end, but they also tell us that. They say the Taylor series above can be used to represent f of 1.2 as an alternating series. So if we do f of 1.2, they say use the first 3 non-zero terms to approximate f of 1.2. So we need to take this guy. Do I need to plug in 1.2 here? Not really. I already have the first 3 terms, right? So what am I going to do here with the first 3 terms if I want to find f of 1.2? Says f of x is equal to this equation, right? But we want the first 3 terms. What are you going to do with the 1.2?
Plug it into the first 3 terms.
Plug it into the first 3 terms for x, right? If you wanted f of 5, you do that. Also, question, to approximate an alternating series, it really should converge. Is it converge at 1.2?
Yeah.
What's your interval of convergence? -1 to 3. Is 1.2 in that interval? So do you even have to consider whether it converges there? No, you know that, right? You just figured out the interval of convergence is -1 to 3. So it definitely converges here. So plug in 1.2 into the first 3 terms. So that's the first 3. We don't need to go up to the cubic term. That was the 4th term. They just asked for the first 3. I'd let you use a calculator on this probably. If it was free response, you could just leave it that way. But if you did use a calculator, you would get 0.905. So we just used a 2nd degree Taylor polynomial to approximate 1.2, right? We said using the first 3 terms, so that's a 2nd degree Taylor polynomial because the highest power was 2. We're using that to approximate f of 1.2. Now that's the first 3 terms. So is that an exact value of f of 1.2? Is that the exact value? Since this was an alternating convergent series, you know the maximum value this is off, right? Where do we look? If this is not perfect, right? This is not the exact sum or the exact value of f of 1.2, right? How do you figure out what the maximum this would be off by? The next term, right? Remember with the alternating series that converges, you just have to look at the next term. So which term should we look at? Yeah, which one is the next one? This one right here, right? Okay, so figure out what that is. We know, because we know that if you take the actual value, f of 1.2, and you subtract what we just found, our approximation, it's going to be less than or equal to, that error will be less than or equal to the next term. So plug in 1.2 into your next term. So that's going to be, and it's absolute value because we're looking at errors, right? 1 over 2 to the 3rd times 3 times 1.2 minus 1 cubed. Technically, you can do this math without a calculator. It's not hard, but I'll just tell you right now it's 1 over 3,000. And they want us to show that our approximation is within 0.001. So this approximation, this would be the maximum. This is off, right? Is that within 0.001? 1 over 3,000? Is that less than 1 over, this is 1 over what? 1,000, right? Is this less than that? Yeah, right? This is less than 1 over 1,000. That's the same thing as 0.001, right? So check. Our error cannot be off more than 0.001 because it's going to be less than 1 over 3,000.